Good day to all of you. Today we shall solve question number 5A in model question paper set 2 of the subject digital design and computer organization with subject code BCS302. So this belongs to module 3. The question is, describe the big-endian and little-endian address assignment. So this carries 5 marks. Solution. Endianness means the order in which bytes of a word are stored in memory. Okay. In little-endian, lower order bytes of the word are stored in lower order addresses of memory. In big-endian, lower order bytes of the word are stored in higher order addresses of the memory. So, in little-endian, higher order bytes of the word are stored in higher order addresses of memory. But in big-endian, higher order bytes of the word are stored in lower order addresses of memory. Okay. What is this? We can understand when we go through an example. So let the example word be 12583946. So these together form 1 byte. Here in this number, this digit takes 4 bits and this one is 4 bits. 4 plus 4 bits means 8 bits. So these two together form 1 byte of the word. So this word is 1, 2, 3, 4 bytes word it is. Means we are dealing with 32-bit words. So 32-bit word means it has 4 bytes. Okay. So this is 1 byte, 2 byte, 3 byte, 4 byte. So this is the example word we have taken of 4 bytes long. Then let the memory location address be 1000, 1001, 1002 and 1003 where this word is going to be stored. Means memory is byte addressable. In one memory location only 1 byte we can accommodate. So for this byte 1 memory location, for this byte second memory location, for this byte third memory location, for this byte fourth memory location. So to store this in memory, 4 memory locations are needed. So those memory location addresses we are taking as 1000, 1001, 1002, 1003. Next, if this is the data word, this 46 is lower byte of the word or lower order byte of the word. This is higher order byte of the data or word. Here in the address 1000, 1001, 1002, 1003, this is lower order address. This is higher order. So with this understanding we shall see next. This and this figure shows 4 memory locations in each. So this is 1 memory location, second, third, fourth. So 4 memory locations here. Likewise 1, 2, 3, 4. Same memory locations. 4 memory locations are shown here. Now 1 byte means 1 memory location. Another byte means an second memory location. This one in third memory location. This one in fourth memory location. It is going to be stored. This way, this 4 bytes of word requires 4 memory locations. In each memory location, 1 byte can be saved or stored because memory is byte addressable. That is what is the meaning. Next, what 1000, 1001, 1002, 1000 and 1003 memory location addresses we have taken, they are written here. So this memory location address is 1000, 1001, 1002, 1003. So 4 consecutive memory locations. So in that this one word, this way it is stored. This way means how? This is higher order byte of the word that is stored in higher order addressed memory location. So this is higher order address. This is lower order address. In lower order addressed memory location, lower byte of the word is stored. In higher order addressed memory location, higher order byte of the word is stored. This kind of storing is called as little-endian. Okay. In big-endian, in lower order addressed memory location, so then higher order byte of the word is stored. In higher order addressed memory location, lower order byte of the word is stored. Just reverse of this. This kind of ordering of bytes of a word in memory, it is called as big-endian. So first, what is endian? The order in which bytes of a word are stored in memory, that is endianness. Little-endian means lower order byte of the word is stored in lower order addressed memory location, and higher order byte of the word is stored in higher order address memory location. But in big-endian, higher order byte of the word is stored in lower order addressed memory location. Lower order byte of the word is stored in higher order addressed memory location. So this is what is little-endian and big-endian. So this is with respect to one word of data, which consumes 4 memory locations for storage, 4 consecutive memory locations. So in general, let us discuss about little-endian and big-endian. So this is the figure of many memory locations, and here also the same number of memory locations are shown. So in general, to discuss about big-endian and little-endian, here this memory location with respect to little-endian and this figure with respect to big-endian, that is continued here, that discussion. So here 0, 1, 2, 3 are 4 bytes of the word 1. 0, 1, 2, 3 are the 4 bytes of the word 1. Okay, the same word here. Then 4, 5, 6, 7 are bytes of word 2. 4, 5, 6, 7 are the bytes of word 2. 4, 5, 6, 7. Here one word is stored this way, second word, and the same are stored in this way in big-endian here. Word 1 and word 2 addresses are 0, 4 respectively. So word 1 address is 0, word 2 address is 4. So it is also same here. Word addresses remain the same. But lower order bytes of the word are stored at lower order addresses in little-endian. So here lower order addresses, in that lower byte is stored. Okay. So 7 is bigger here, but this is lower order address. Here lower byte of second word is stored. In higher order address, higher order byte of the second word. Here higher order byte of the first word. Here exactly reverse. In lower order addressed memory location, higher order byte of the word is stored. That is of word 1 here, word 2 here. So these two figures show in general the little-endian and big-endian type of arrangement of bytes of word in memory. Okay. Then question number 5b. Demonstrate the instruction execution and sequencing for C equal to A plus B with block diagram. 8 marks. So this is symbolically showing the instruction C equal to A plus B. So content of A memory location is added with content of B memory location. That is what is the square bracket indicates. That is stored in memory location C. Okay. So demonstrate the instruction execution and sequencing for this. Right. Solution. So this is the block diagram for the asked question. So these are the memory locations where contents are shown here. So this is first memory location content. One instruction is stored, and second memory location, second instruction. Third memory location, third instruction. C equal to A plus B needs these 3 instructions, and these are written in assembly language here. Let I be the address of first memory location. Then next memory location address will be I plus 4 because each word will be 4 byte long. And memory is byte addressable. To store 1 byte, 1 memory location is needed. To store 4 bytes, 4 memory locations are needed. So to store this instruction word starting at I, 4 memory locations will be taken. So I memory location, I plus 1, I plus 2, I plus 3. So that is this. Then second instruction word address will be I plus 4. Third will be I plus 8. Next in memory we can see 3 memory locations. Their names are A, B, C. In A and B operands will be stored and they will be added and the sum will be stored in C. That is what is content of A is added with content of B and it is assigned to memory location C or it is stored in memory location C. So this is the data for program, that section. This is the data. This is 3 instruction program segment. Okay. Execution begins here. First this instruction is executed, then next to this and next to this, means sequentially one after the other these 3 instructions are executed to get C equal to A plus B. So what is happening in this instruction? Move instruction will copy the content. This is source, this is destination. So from A memory location to R0 of register. So from here it is copied to R0 register of processor. Next add B, R0. Add will do the addition. This is source, this is destination. 2 numbers means this content and this content it will add and result it will store back in R0. So add B, R0. So B memory location content is added with processor register R0 content. So in this instruction has stored in R0 A. Hence here B is added with A and the result is kept back in R0 only. Move R0, C. So it will copy the content of R0 register. What is there? A plus B. So that to memory location C. So this is what is the sequence of execution of these 3 instructions and how these 3 instructions when executed will give C equal to A plus B. So here C is content of A plus content of B memory location, means content of memory location A is added with the content of memory location B and result is stored in memory location C. It has 3 instructions: move A, R0 at I memory location, add B, R0 at I plus 4, move R0, C at I plus 8 memory location. Means we are describing this block diagram. Here it is assumed that word length is 4 bytes. Hence each instruction word occupies 4 locations. The 3 instructions are in successive memory locations. Figure shows a possible program segment for this. Program counter PC holds always the address of next instruction when a program is being executed. Through PC, processor control circuits fetches and executes instructions one at a time in order of increasing addresses. This is called as straight line sequencing. Means first it will execute instruction at memory location I, then at I plus 4, then at I plus 8. Each time when an instruction is being executed, program counter will store the instruction of next address. Processor control circuit will utilize this. So hence in sequence the instructions of the program will be executed. That is called as straight line sequencing. Okay. During the execution of each instruction, the PC is incremented by 4 to point to the next instruction. Executing a given instruction has 2-phase procedure. In first phase called instruction fetch, the instruction is fetched from memory location whose address is in PC. This instruction is placed in instruction register, that is IR of processor. In second phase called execute phase, instruction from IR is decoded by instruction decoder and executed, and PC is incremented by 4 to point to next instruction. Okay. So execution of one instruction has 2 phases, fetch and execute. So there are 3 instructions, one at I, another at I plus 4, next at I plus 8. So PC at the beginning will point at I. So at I move A, R0 instruction is there, that is fetched from the processor and it is put into instruction register of the processor. Then PC will be incremented, program counter will be incremented by 4. So it will point to next instruction I plus 4. But now which is already fetched and kept in IR, instruction register of the processor, that will be decoded and it will be executed. So when its execution is over, second instruction is already, its address is there in PC, that is utilized by processor control circuit. So it will fetch that second instruction. So then PC is incremented by 4, it will point to third instruction. Then second instruction is decoded and it will be executed. After that, third instruction address where already it is in PC, that will be fetched and it will be executed. This way every instruction has two-phase procedure in its execution, that is fetch and execute. So this is what is the demonstration of the instruction execution and sequencing for C equal to A plus B with block diagram. I hope you understood. Thank you. So next we shall discuss question number 5C with a block diagram. Explain the basic functional units of a computer. This carries 7 marks. Solution. So here the diagram for basic functional units of a computer is drawn. So there are 5 blocks here or 5 units. The first one input, here output. This is called as IO block, input output block. There are 2 units, input output, and this is memory unit, and here this is processor block. In that 2 units, arithmetic and logic unit and control unit. So 5 units we can see. They are basic functional units of a computer. A computer consists of 5 functionally independent main parts: input, output, memory, arithmetic and logic, and control units as shown in figure. So let's say about input unit. Computers accept coded information through input units which read the data. The most well-known input device is keyboard. Other devices are mouse, joysticks, and trackballs. Next, output unit. Output unit sends the processed results to the outside world. Example: printer, plotter, graphic displays. Both input and output units are electromechanical devices. Next, memory unit. The function of memory unit is to store programs and data. There are 2 classes of storage called primary and secondary. Primary storage is fast memory that operates at electronic speeds. Programs must be stored in this memory while execution. This memory is volatile in nature, faster but costly, and hence it is implemented in smaller sizes. Secondary memory is electromagnetic, less costly, hence is provided in bigger sizes, but it is slower and not volatile. For permanent storage, programs and data are stored in secondary storage device, that is hard disk. Okay. Control unit. It controls and coordinates the activities of all different parts of a computer, that is input, output, ALU and memory, and all IO devices. For this, it sends control signals to all parts and senses their states. All the activities inside the machine are directed by control unit. ALU, arithmetic logic unit. Most computer operations are executed in ALU of the processor. It performs all arithmetic and logical operations. Input and output devices both are electromagnetic devices. Input is used to give data and instructions to computer, and when it processes and what results it gives, interpret that result in user understandable manner, output devices are used. Here keyboard, mouse, joysticks, trackball, they are the examples for input devices. Printer, plotter, display devices, they are example for output devices. Memory is used to store data and instructions. There are 2 types, primary and secondary. Primary memory is electronic memory. It is faster but costly. Hence in smaller sizes it is provided. Secondary storage devices are cheap. They are made up of electromagnetic material. they are less costly, hence in bigger sizes they are provided. Secondary storages are non-volatile, but primary storage memory is volatile. But during execution of a program, both program and data must be in primary memory area only. Okay, that is why during execution that is loaded from secondary storage, that is hard disk to RAM area, that is primary memory. These two are the two parts of the processor: arithmetic logic unit, control unit. Control unit senses the states of different parts. It sends control signals to different parts so as to control and coordinate the activities of those. Arithmetic logic unit performs arithmetic and logical operations. Okay. So this is all about basic functional units of a computer. So that completes the discussion of question number 5 ABC for a total of 20 marks. I hope you understood. Thank you.